All right, so the next session is Flying into Virtual, the new reality for aerial education with robotics. It's by Andrei Kordigotsky, Oleg Kalachyev, Alexei Rogachevsky, and they're calling in from Moscow. Team Copter Express is a development and manufacturing company of open source, and the company's quadcopters are designed for educational purposes, autonomous serving, and also aerial parcel delivery. So in 2019, over 1,600 Clover drones were sold worldwide. The last year at the Dev Summit, they presented PX4 in STEM education, how we taught 1,000 students to program with drones. And this year they're back with an update into flying into virtual. All right, guys, let me just switch to your screen. You're here.
Okay.
Can you do a quick mic check before I let you go?
Yes.
Hello.
Hello.
Hi.
We can all hear you. Hi. All right, go ahead, guys. Thank you.
Okay, thank you, Ramon.
Thank you.
My name is Andrei Perigotsky. I'm CTO of Copter Express. In Copter Express, we are focusing on the drone education. And today we will tell you how we adapted our educational products and activities to the new reality of education during the lockdowns. During the session, I and my colleagues will briefly describe our platform and educational activities, discuss new challenges that educational robotics face now, and then my colleagues will discuss in detail the simulation environment that we use based on Gazebo and how we deliver it to our students. Our main product is an educational drone kit called Clover. It's a kit with PX4 Autopilot and Raspberry Pi, which we ship disassembled as a set of parts and used to teach students in school, colleges, and universities how to assemble the drone, how to fly it, and how to program it to perform different autonomous tasks without remote control, like locating some objects, grabbing it, replacing, moving to other location, etc. We presented our platform in detail during the previous PX4 Summit. You can check out the video from previous summit if you are interested in details. The idea of our platform is to lower the barrier of entry into the field of flying robotics to make it really open, both open source and not too complicated to understand for students without heavy robotics background. You can just take our kit, assemble it, insert a micro SD card with our image and take off with just one line of code. Even if you don't know what SH is, you still can use Clover's web interactive shell. That's how awesome Clover is. All that you can see here on the video is performed on our software platform. It is open source and you don't need to buy it to use. You can assemble virtually any drone with PX4 Autopilot and Raspberry Pi companion computer and flash a micro SD card of Raspberry Pi with our image and you are good to go. You can fly autonomously with just one line of code. If you want to use different companion computer, you always can just get our ROS nodes, which are open source, and use it on your setup. This is a really popular product in Russia, and now we're expanding worldwide. So the Clover platform is used all over the world, and I think it's by far the largest PX4 educational product because it's being used by more than 10,000 students to teach how to make drones. So all of videos which I shown were pre-lockdown videos, and of course lockdowns affected education heavily all over the world. Just a few months ago, online education was, although quite common, still something unusual, and now it's a new standard. In a flash, everything went virtual. Our job is to gather the most of the positive impact of the events which is happening. Robotics education always were in person because, of course, robotics is about robots and you need to physically interact with your robot. So this is really a challenge for robotics education, and we will today talk about how we address this challenge. Stage 0 of our response is online video lectures, both pre-recorded and live lectures. But that's what many have used before anyway, so it's not really new. And you can't address main challenge, necessity of interaction with the robot. Theory is good, but robotics education needs a lot of practice. We used simulation before, but it was never our priority because there are so many things which could be improved in Clover platform to make it better. But when lockdowns begin, we made it our priority and started to develop our simulation environment very, very effectively. And now my colleague, our lead developer, Oleg Kalachev, will talk about our simulation. Oleg, please.
Thank you. Okay, you see the presentation? Do you
Yes.
see the presentation? Okay.
Yes.
So here's gazebo simulation. We created a pretty detailed model of our drone, and you can see it on the picture. And we put a Mavlink plugin and flight controller sensors plugin to it, so it can interact with PX4 instance. Of course, we're not taking any credit of creating the interface between PX4 and Gazebo. We just based on the existing standard PX4 Gazebo simulator, but we only modified it a little bit and added some features we need. So although this work is pretty much under construction now, but it's already used in our educational process, and I will show you what it can do. So our goal is to completely recreate the Clover API, the ROS Clover API accessible to the user through ROS services and ROS topics. It includes PX4 itself through MavROS, our autonomous flights API, which we presented last year, all installed sensors API, camera and rangefinder, our LED strip API, and the rest. For example, web video server for monitoring ROS images topics with the browser. So I will not be risking too much and be showing you the simulation live. So I show you some pre-recorded screencasts. So here you see the simulator running in a virtual machine on a Mac, and I use Python to make the drone fly autonomously using the same commands as on a real drone. So before I entered the standard Clover program header from the documentation, and now I use ROS navigate service for taking off, and the virtual drone takes off. And here you see the simulated camera topic, and the drone now hovers stable using our own ROS-based optical flow as on a real drone. So there is no GPS or any other positioning system. Now I ask the drone to fly forward 2 meters using body-related TF frame. And of course, I can ask it to fly 2 meters backwards. And for example, use the very simple land service that just make it land. Also, another sensor available on a Clover drone is the rangefinder. We use a popular STM rangefinder, and we configured a Gazebo plugin to simulate it completely, including the ranging noise. And here you see another demo. I fly upwards and downwards on a simulated Clover drone, and I monitor the range value from a ROS topic using the standard ROS plotter. All of the data from the rangefinder, of course, should be also used from the user program the same way as in the real life. Another important feature of the Clover platform is RUC markers recognition. Of course, we do it in the simulator as well. So here is the demo. The drone sees an Aruka marker, and then I ask it to fly 1 meter above it using Aruka underline 100 TF frame, and the drone hovers, and then I ask it to land to the marker, and the drone do it. Often we use maps of markers to position the drone precisely and without any drift. We pass this information about the drone position in the map using vision position estimate message and how it works, and that's what it looks in the simulator. You can watch the marker map recognition debug topic, and here I ask the drone to fly to some different positions in the marker maps, for example, 3, 3 here, and then I ask the drone to fly to the point 1, 3, and everything is can be debugged in Aruka map topic, and then, as always, I landed the drone. We also install an LED strip to all our Clover drones to make their flights much more spectacular. And we created a gazebo plugin that completely simulates the ROS API of our LED strip. This allows the user to set different effects to the LED strip, like this rainbow, for example, or I set another effect, wipe to the red color, and you see the red color. Then I set, for example, a blinking effect, and it also works. So all of this works during a flight of a drone. And of course, setting individual LED is also possible with this API. So this API is actually pretty powerful. By the way, if you're interested, this API is documented and open sourced, and you can use it with any compatible LED strip, even without our kit or without our full software package. Also, we can add different models to the world, like these, for example, lines or color circle or something like this, to make some interesting and fun computer vision tasks. And here's another little example of programming a simulator. So now the simulated drone and the real drone does flip, and you can somehow compare how it happens. So we develop everything that I showed you in the main Clover repository, but since it's under development, the work goes in a Clover description branch. So you can check it out if you want. And now Alexei will tell you about how we deliver this to our users. So Alexei?
Yes, thank you, Oleg. So my part of the talk is about delivering the simulation environment to our users. I will tell you about the challenges we've faced and the solutions we've explored. So first of all, let's talk about users. A typical robotics engineer familiar with ROS will probably have a Linux-based system running natively on their hardware, or will at the very least have a virtual machine with their favorite distribution installed and configured. They know ROS simulations may be quite demanding, and thus will probably have a reasonably powerful workstation. They may even know their way around Docker, Rocker, or other container software. And they probably are very familiar with Gazebo, know how to debug their configuration problems, and how to build their own worlds. By contrast, our users are typically those who are only starting their wonderful journey into the world of robotics. They typically have Windows as their primary operating system, with mission-critical software that makes installing other systems not an option. They may be using hardware at their schools or colleges, which is not always as high-end as they'd like. They don't have any experience running Docker or virtualization software and don't really know their way around Linux. In fact, Clover might be their first Linux platform. Our goal is to make their first steps into robotics as painless as possible. So how do we make the simulation environment accessible then? We have several options, each with its own pros and cons. First of all, we may ask users to install Linux on their hardware. This has the obvious benefit of using native hardware and storing the data and software locally. But this is time-consuming and error-prone if done manually. There's also the issue of Linux hardware support, which is not ideal. Each installation would possibly differ, would have its own quirks, and dealing with those quirks may require a substantial amount of Linux knowledge. Then there's Docker, which has been a go-to solution for application deployment for years now. Docker installation is simple, and running a container is a single line in your favorite shell interpreter. But all of that comes with a cost. Since we want GPU acceleration for computer vision, we need to use a native Linux installation. What's even worse is that running a container with GPU support is vendor dependent. That is somewhat solved by wrappers like Rocker, but the experience of running desktop software from a container has so far proven to be less than ideal. There's also the issue of container isolation, which, while generally considered a good thing, may make some tasks like editing files challenging to newcomers. There are also cloud-based solutions, like ROS Development Studio from the Construct. This is probably the most user-friendly option, requiring nothing more than a modern browser. There are several issues with that, though. First of all, there are no readily available open-source solutions. We'd have to put additional engineering resources into developing and maintaining our own system. Then there are additional costs for our customers and possibly for us as well. Hosting would also be a problem, since there are not as many GPU-equipped data centers around the world, and using a high-latency server is an unpleasant user experience. Finally, there's less control over what actually happens on the hardware, much more magic, which, in our opinion, is not a nice thing for an educational product. Finally, there are virtual machines. They are easy to deploy. They may usually be sent as a single archive. All changes that are made to the VM are local. A user may inspect the machine, interact with it as if it was a real one, but with lower risks of data loss. We can pre-configure our machines to have optimized defaults, and best of all, there's no need to change your main operating system. There are still drawbacks, though. A virtual machine requires additional software, such as a hypervisor, and will not perform as well as the native solution. GPU virtualization is not perfect as well, which is a pain point for us. So our solution for now is actually to use a virtual machine. We need a hypervisor that supports multiple host platforms that provide GPU acceleration. It should also be free, at least for personal use. The two options that we've found so far is Oracle VirtualBox and VMware Player. So first we've tried VirtualBox, but its issues such as rendering errors and overall unsatisfactory performance have prevented us from using it. And so we come to VMware Player. VMware Player is another free for personal use hypervisor. Sadly, it does not support macOS, which makes the users buy licenses for VMware Fusion or Workstation. Other issues are not present, though. The driver for virtualized GPU is built into Mesa. Guest tools are packaged for Ubuntu. There are still some issues with Gazebo that force us to limit virtualized GPU to OpenGL 2.1, but we hope that this will change soon. As such, VMware Player is our hypervisor of choice for now. We strongly believe builds should not be done manually, so we're using HashiCorp's Packer to automate our virtual machine builds. We use VirtualBox to build the VM and export it as an OVA archive. This archive can be imported into VMware, and with some OVF tweaking, we can make the VM with reasonable default parameters. Current build scripts are available in our repository, and the resulting image is available for download. As for the contents, well, Oleg's demos were performed in the simulation environment with minimal customization, and the very same image is being used as we speak for our courses. So that's it from me. Andrei, take it from here.
I don't hear you, Andrei.
Hello.
Yeah.
Great. So we rely really heavily on the simulation now, and it is stage one of our solution to the education during the lockdowns. We use simulation during the courses, both for students and for teachers. For example, on this slide, you can see the execution of the task when the student should have take from one cube and land on another, recognizing it using computer vision. Yeah, so we use simulation really heavily now, and it's really helps. But it's not everything. Because the world is much more complex, and despite all our efforts, simulated world differs widely from ours. So when our students can run their programs in the simulated environment successfully, we still need to somehow test them using real drones. But all of our educational institutions are closed, so we need to use remote controlled drones. So we use the controlled environment either in our office or in some other educational institution in which our employees or another tutors facilitate the running of the test programs on the drones. So the drone can fly in some environment in our office while the person who wrote the program is in many kilometers away. We use it for courses, and we are now preparing course in English with simulation and with usage of real-world drones, which are remote controlled. You can check it out on our Square website, and you are also welcome to check out our preliminary Kickstarter campaign. The link is below. So on this video, you can see how the person competing in the drone competition, which was just 2 months ago, controls the drone remotely, and the drone can perform some task in real world using the program which was created by many kilometers away. Yeah, and here on another video, you can see another competition when guys programmed the drone to fly autonomously using the Clover platform. You can see the debug screens here. Yeah, so they used OpenCV to program the drone flight, autonomous flight using the Clover platform, and then run them remotely. So our solution to the education during the lockdowns are online lectures, simulation, and remote controlled drones. So yes, lockdowns are bad thing overall, and the pandemic is of course bad, but we need to get the most of the good part of it, because it really catalyzes the transformation, the going to virtual, and so we can use it to push virtual education, to push using of simulation and other different modern techniques to educational institutions, which are usually quite conservative and want to have real lessons on site and are quite closed for new modern things. So use this moment to get it. Use our open source platform. We are very glad when everyone use it, and good luck with your educational projects. We are open for any questions. Yeah, 1 second.
Okay, so Ramon, will you read them or? Okay, can we replace remote control with mobile operating operating using an UDP port for indoor use. Can we?
Well,
I mean, So you mean to operate the drone from away using UDP? I mean, not locally, but remotely. I think it's possible, but the ping would be very big. Maybe 5G will help with this. So, anyone?
Thank you.
Do you want to tell something about this?
Yeah, the next question is, can we use OpenCV or other object detection libraries? And yes, of course you can, and it's part of our curriculum. So we even teach how to use OpenCV with our libraries and our ROS nodes. But you can use whatever you want. If it works smoothly with ROS, it's great because our simple of board node is ROS node and you can communicate very smoothly. But you can use virtually anything that will run on your companion computer with our ROS packages to perform some autonomous tasks using object detection libraries. Yes, we create the platform exactly for use cases like this.
And the third question is for Alexei, I think. Alexei.
Well, any plans to support ROS2 in the future? Well, I guess it depends on your definition of future. For now, we are on ROS Melodic and are transitioning to ROS Noetic, the last ROS 1 release. Well, eventually we, of course, we will have to transition to ROS 2, and we will probably embrace this transition as well. I am personally really excited about that and about the PX4 and ROS 2 integration, but that's, I guess, not in any concrete plans right now.
Okay, I can read the fourth question. Is there a gap between simulation and reality? What challenges did you face running simulated code? I mean, I think it's if there is some simple task like flying from from one point to another, there's almost no difference because the simulation works pretty good in this task. For example, if you're working on very complicated computer vision problems, then the rendered 3D world can differ from the real world, but this is still useful, I think.
Yeah, I think I'll probably talk about it a bit more. Sometimes you tend to bump into some of the simulation quirks, like Gazebo not actually Gazebo sensors not providing you your sensors with a constant update rate, but rather giving you an option to provide a highest bound for your simulated sensor. So in case of cameras, if you for some reason don't have a GPU acceleration on your system, and you want to place a camera that's you would want to provide like to publish an image 30 times per second, there can be issues when the most that your hardware can do is actually 5 times per second, and for some reason Gazebo will not always slow the simulation down. So there's that.
Awesome. Thank you, guys. Thanks a lot for your
I think
help
maybe
today.
maybe we should ask Svetlana for something to tell about her experience, because I think she should say something. So what's your experience about remote competitions?
Thanks for your question, Oleg. My experience, it was very interesting for me and for our team, because we don't have any students locally in our office where we make a remote controlled launch of the drones. But it was a very crazy thing because we create system control without manual control, only autonomous flight, only using code from our students, and they need to give more information from each flight at the polygon in our competition. It's good opportunities in our current time with pandemic. And also, I saw a question about using LTE or EKF. We use both LTE or EKF too. Thank you.
Okay. Oleg could answer this question, but I really think our time is up. Yeah.
Yeah. Hey guys,
So-
sorry to cut you out, but our
Okay, no
time is
problem.
up. Our next speakers are waiting. Thank you.
Thank you.
Team Copter Express.
Thank you. Very pleased.
Yeah.
Really
See you soon. All right. Hey guys, I'm back. Can you guys hear me okay? Yes, audio levels are good. Guess what? We're still live. So I'm back. I'm Ramon Roche. I'm the program manager for Drone Code. We just heard from Copter Express. Thank you guys. That was great. I really look forward for those slides with all those resources in them. I will share them via Sket soon. Guess what? Next up, we got overview of multi-copter control from sensors to motors by Matthew Berscani and Matthias Grob from Autherian. They're also returning speakers for 2019. They're members of the PX4 Dev team, and they're joining live from Zurich, Switzerland. Give me a moment while I connect with them. I'll promise I won't take that long. Be right back.